The purpose of this video is to give you an introduction to the difference between integral versus differential analysis while describing thermal fluid systems. So the system we're looking at here is a gas turbine engine, often called a jet engine if it's on an airplane. Power generation systems more often refer to them as gas turbine engines. We're actually going to give you a deep dive into gas turbine engines later in MC312, but for right now I'm going to give you kind of a crash course just for the sake of providing an example to describe integral analysis. So in MC311 we actually describe the components of a gas turbine engine as three separate units. First of which is a compressor on the left hand side, a turbine on the right hand side, and then we had a combustor in the middle. Now we had fluid comes through the compressor, air in this case, then feeds into the combustor where heat is provided to the system, and then hot air goes into the turbine and expands across the turbine, producing useful work. So that useful work turns the shaft, which turns the compressor and completes the cycle. Now for integral analysis, what we're really interested in is actually just drawing a control volume around this entire system and then worrying about essentially how much mass and momentum enters and exits the system, in addition to how much mass and momentum potentially gets stored inside of the system. Now with that said, all of the components inside of the system we're actually not that worried about. We're really just treating this thing as a black box. So whatever is actually the intricacies of what's happening inside, we're not that worried about. So our first equation that we're interested in for integral analysis is what's called conservation of mass. So the first term in this equation is our statement of the rate at which mass is accumulating inside of the control volume. Now if it's operating at steady state, we'd be able to say that this deal is equal to 0. If we have mass entering and exiting the system, say we have mass m dot in, and we have mass flow exiting the system, then the continuity equation here is equal to our mass exiting minus our mass at the inlet is equal to 0. And the other equation that we're interested in is our conservation of linear momentum. Now, conservation of linear momentum in this case, let's imagine that we have taken this jet engine, which is really just a black box, and we've said we need to basically bolt it to the ground. Now, because of our exhaust that's pouring out this backside of this system, we would know from our friend Newton that we would equal and opposite reactions, right? So we'd end up having a force of thrust that would be pushing the engine to the left, and if we were to bolt this thing to the ground, that means we must have a force holding it in place. So that is described on the left-hand side of this conservation of linear momentum equation. And on the right-hand side, we have another statement of the rate at which momentum is stored inside of the control volume and the rate at which mass, or in this case momentum, enters and exits the system. Now the thing I want to emphasize and go back to emphasize is that integral analysis really just cares about what's entering and exiting this control volume. And as the red line would show, entering or crossing that control surface. We're not as worried about the intricacies of all the components on the inside. Now, if we want to dive into the details of the components, what we need is differential analysis. So let's again step back, look at this device, or this engine rather, see all of the intricate components, and now let's zoom in on the combustor to see how differential analysis might play a role in understanding this system. So if we have mass that travels through the compressor, down through here, right? And then into the combustor, and we have all this amazing swirling mixture of air and fuel that then gets combusted and burns very hot and then runs through these turbine vanes. And those turbine vanes are essentially airplane wings right? So they're formed roughly like that, and they're designed to help push air down or in one direction, and as a result, they get a net force in the opposite direction. That produces the work that they are able to then use or extract from the flow of the hot exhaust to then turn the shaft, which subsequently turns the compressor. Now, a couple of quick things to point out, right? We can use differential analysis to describe all of this complicated flow that's moving through the compressor, into the combustor, and then through and over the turbines, blades, and vanes. We can also use differential analysis to, say, describe boundary layer growth on those turbine components, and maybe even separation, right? You've seen that in class. Now, one thing of DTAMs that I want to point out is notice the direction of this animation. In reality, it should be spinning from left to right. If you notice the shape of those airplane wings, or the shape or the equivalent of what those airplane wings are, they're really all those turbine components that are spinning, and it looks like they're spinning from right to left, but they should actually be spinning left to right. I point this out because as engineers, we need to always have our guard up. We need to always be doing DTAMs. We need to be always checking whether or not things are making sense, despite trust but verify is what we always need to be doing. And differential analysis can help us do that. So here's a couple other examples. In this case, we have a centrifugal pump with flow coming into this system, entering here, and then spins around radially, and then gets ejected from the pump housing. So this component that's shown on the right is actually very similar to the pump system that gets used in your design of experiments for the pipe friction demo lab that you're analyzing actually right now. So differential analysis, we would be taking infinitesimally small sections and we would be tracing this fluid as it comes through this section. And we'd be doing the same here, right? We'd be considering all of these tiny differential elements inside of here and how fluid moves through them in order to analyze this pump. To give you another example, let's consider rocketry. On the left-hand side, let's say this is an integral analysis problem. If you're not aware, this is SpaceX. This is their Falcon Heavy system. We're going to draw a control volume around this rocket. And we have all of this exhaust pouring out the bottom, all of this mass and momentum that's getting shot down. And in the opposite direction, we end up having a force of thrust that pushes the rocket into the sky. Now, the integral analysis, we're really just cared about the macro scale, right? Just the amount of mass and momentum that crosses the control surface and what's happening inside of the control volume. On the other hand, let's zoom way in and consider a differential analysis problem. In this case, maybe we're interested in all this amazing stuff that's happening in the exhaust. And maybe we zoom way in. We zoom way in and we look at one of these differential elements that's inside of the exhaust. That's defined as dx, dy, dz. And we have all this mass and momentum that's crossing through the control surface. So we care about the micro scale in this case. Now, the value of understanding all of these differential analysis approach is that we can use it to do computational fluid mechanics. And that's really useful because we can map fluid flow through a component like this pump housing that we're seeing here and understand at each individual component where the pressure is, what the velocity of that fluid flow is, etc. We could also map extraordinary things like vorticity shedding even off of the wings of, say, modeling in this case, the wings of a hovering hummingbird, which I find to be incredibly beautiful. Now, for our application, the U.S. Army, right, we could also use very similar concepts rather than vorticity shedding off of a hummingbird wing, but instead see, say, vorticity shedding off of the tips of the rotors of a quadcopter, or quadcopter. So in this case, what you are seeing, similar to what we talked about in your lift and drag lectures, you are seeing basically tip vortices that are forming off of these rotors, which is quite remarkable for what we can use for fluid mechanics for. So if any of you are interested in grad school, this is the type of thing that you can begin to explore if you want to dive further and further into this field. So let's do a quick rundown of integral analysis versus differential analysis. Integral analysis, we're talking about the macro scale, big stuff. Or at least we can analyze small stuff, but really we're more interested in like averages is what I mean by big stuff. So say we have some control volume, we have fluid and momentum traveling into it, and we're treating it essentially as a black box. This is a black box, but it is still very useful. We can get, we can get thrust, we can get conservation of mass, we can get all sorts of very useful stuff using integral analysis. Differential analysis. This is more akin to, say, microscale. So in this case, we might get, say, a boundary layer off the surface of a wing. And we do that by focusing on the minutia, by zooming in to these tiny elements, dx, dy, dz. And from that, we might be able to, say, map what the boundary layer looks like over a wing. So in the next video, what we're going to do is we're going to dive into differential analysis, and we're going to talk about how we use it to derive conservation of mass.